Some ruminations. I'm a ruminant today on a couple of points. And the 2 points I want to make, I'll tell you ahead of time. One is that intermittent things are really a pain because they come and then they're intermittent and they don't come again, and maybe that was the real thing. So I want to just this is my hobby horse in this business, and all of us who have done SETI have suffered with this. And the other one is I just want to sketch out a scheme for doing all sky optical all the time, kind of a friendly amendment to Elliott's talk. So I'm going to zip through this pretty fast because I think most of you are familiar with this, and we've been hearing it, and we will hear more of it. The classic window shows the radio window and the optical window. I would say that really we want to think also about some of this stuff here, the infrared. Just because we happen to live under an atmosphere is not a reason to stop thinking about what we could do when we're outside it. And since we're talking advanced civilizations, they're going to expect us to grow up. But anyway, talking about these two windows, and we've heard this before. Jill mentioned the famous Guyon-Marson article in which they looked at the entire spectrum and came down with the only place to look here is 1420 megahertz. I think we've kind of broadened our view, but at least back then that seemed like such an obvious thing, and particularly because that puts you in this minimum of noise temperature owing to things like atmospheric absorption emission lines, particularly galactic synchrotron radiation, and also the cost of quanta. And just a tiny piece of history here. Avi was talking about cool stuff that happened at Harvard. Well, finding this 21 centimeter line right there actually happened at Harvard. And here's radio astronomy, 1951 style. That's Doc Guyon up with his horn there, which with this apparatus here, that's radio astronomy technology, 1951, was able to detect for the first time the 21 centimeter neutral hydrogen. I'll just show you this because the history is so cool. This is Ed Purcell's grant proposal, or at least the first part of it. Somewhat different from proposals nowadays. It's 2 pages long. And he says here, and also he writes it so charmingly, microwave radiation of this wavelength can be absorbed or emitted by free neutral hydrogen atoms, of which interstellar space contains a supply abundant for our purpose. I just love that kind of writing. I don't think you're allowed to write like that anymore. Anyway, here's the second page, and here's where the budget comes. Sticker shock here. Here's the budget. $500 is what I needed to do this experiment, and the $500 got this. This is the first, this is within a few weeks of the first detection. That yellow line wiggling up and down over the drifting baseline is the 21 centimeter line. It has a differentiated shape because of Dickey switching. Okay, so anyway, a little bit of history there. So Guyon-Marson said do 21 centimeters. Frank Drake, who actually hadn't read their paper, was doing 21 centimeters, and everybody gets into this, and we got into this too. Let me just do the nerdy slide here with the equations. You can't mess up these equations with a Macintosh. This is the classic thing, a couple of Arecibo's, 1,000 light years, and you write down some equations. I call that thing a nerd box because it's all in there. You transmit $1 worth of electromagnetic radiation, take the gain, take the fraction of the 4 pi steradians, and you wind up with 2 times 10 to the minus 11 ergs arriving at the destination. That's not very much. This is the cute thing that says it's the punchline that matters. And the punchline is the 10 to the minus 11. That turns out to be about 1 trillionth the energy of a falling snowflake, if you like these humdrum analogies. But KT is much lower. The KT for a reasonable system temperature is 1,000 times lower, and the consequence, 10,000 times actually, that you're doing quite well with $1 worth of electricity, and you can send interstellar telegrams for cheap. So many of us got into SETI through this route, and just like L.E. Tarter in the movie, I too was a ham as a kid, and then grew up to be, and got a big antenna. This is actually the control room at Arecibo back in 1978 when I had a sabbatical, and Frank Drake kindly allowed me to go down there and play. And then came back to Harvard and got this thing, and that's my son Jake. So this is a nice dish, and this is what we use to do our radio SETI, sponsored mostly by the Planetary Society and somewhat by NASA. This is our beta project that you see there. That's the billion channel extraterrestrial assay, so-called. Well, we did this kind of stuff, and just again, now I'm going to get into this thing about redundancy or intermittency. Here's the abstract title page of a paper that I wrote with Carl on the findings of 5 years of this. And what it found, and a little hard to read the abstract there, but basically there were when you cleaned up everything and got rid of all the stuff that was totally fishy, I hope you didn't throw out the baby with the bathwater, you wound up with 37 unexplained events that did not repeat. And there's how they look on the sky. And it didn't do too much for SETI, but it did, in the food chain of SETI, the company started up and called itself 37 Signals. There's their logo. I'm not quite sure what they sell. It's not signals from space. But here's the point, which is that none of which has been detected upon reobservation. And that's kind of what SETI people have been doing now for decades, which is having occasional things that don't repeat upon reobservation. How sad. Too bad there weren't two observatories pointed at the same place at that time. Let me switch to the optical, where I think I'm going to show you a similar lesson. And so I think Jill made this point that the Guyon-Marson paper was the year before the invention of the laser. And so when they talk about, it's hard to read on this tiny screen, that they said, what kind of, could you do it in the optical? It would take a very big, elaborate apparatus. We can't imagine doing that. Well, that's because there weren't yet lasers. But the next year, 2 years later, is the Schwartz and Townes paper, because 1 year later was the discovery, invention of the laser, or optical maser, as Charlie Townes liked to call it. And then we have this paper here from Townes in 1983, in which he sort of went through the calculation and showed that if you really take into account antenna gain, directionality, and backgrounds and all that, that it's really not a correct statement that nature favors microwaves and that optical really is no good. It really is. It's really quite competitive. Not to say that it's the preferred one, but it's certainly in the ballpark there. And even Frank Drake signed on to this. There's Frank standing on top of our radio dish, but doing optical SETI. You see. So let's see. Let me show you the equivalent calculation here. Nerdy slide number 2, which is that, as Jill mentioned and Elliot did also, that a bright laser with reasonable directionality is a darn bright thing. Here's the original thing, and I'm not talking about Ali Javan's 15 milliwatt helium neon laser, which you see here, but something really big, like this proposed solid state diode pump laser designed for fusion pumping. And this thing will put out a petawatt for a few nanoseconds. And you can do a lot with a petawatt with a few nanoseconds. Oh, this is a cute little graph showing progress in lasers over the years. So here's some of the small gas lasers, and then you get up to this, you get to these diode pump things. And this is units of terawatts, so that's 1,000 terawatts. This is a lot of power. Just to give you a sense, this dashed line is an extremely accurate graph of the entire electric power production of Earth. And I know it's extremely accurate because I used one data point here, and I used one data point here, and I drew a straight line. You can even see the little dip here during the California energy crisis. So this is a powerful laser, but we can do these things, and then you get a lot of stuff delivered on target, and you've heard this result before, but basically it outshines the light from your star by a factor of 10,000. And that's good, because it means that if you observe for a brief period of time, the star is dark and the laser is bright. The star disappears. I think these points have been made, but at optical, you get a lot of antenna gain. Pulses, unlike at the radio, are not highly dispersed by the interstellar medium. Jim Cordes has done some nice work on that. Lasers are getting powerful. Lots of bandwidth if you actually want to say anything. And the detection's rather simple. Here's a little, show you that one before. Here's the first apparatus we put together, learning from the lessons that Dan Wertheimer had done with his, I think, really the initial first experiments on this kind of thing. So we put together an experiment, and we picked a nice dark spot in the world. Now here's the world, brightness of the sky. And where would you pick? Well, we first decided we'd like to be in the continental US, and then we decided we'd pick a nice bright spot like here, right here. Okay, that's Boston. We're about here, actually. So not the best choice of places, but nice and accessible, and easy to go out and fix things and improve your experiments. So it's great for students, and it's actually great for grown-ups too. Not to say that students aren't grown up. Well, anyway, so here's our experiment. This was the first one. It used that ancient-looking thing that was built in the 30s, a 61-inch telescope. I'm told it was 61 inches because it wanted to be the biggest telescope, and there was the 60-inch Mount Wilson around, so I had to go 1 inch bigger. Anyway, there it was, and we looked at a bunch of stars. In fact, we were piggybacking on the experiment by Latham and Stefanik, who were examining stars for SETI purposes. And let me just show you some results here. And this is in that paper by Howard et al. A little bit of explanation. We observed about 4,000, a little over 4,000 objects. Most of them gave us no hits at all, where a hit was something cleanly defined as something that really looked like an optical pulse. 179 objects actually gave us one such thing. 15 gave us 2, 5 gave us 3. But if you notice here, the observing time went up. The ones that gave us more hits were observed for longer periods of time. So you might ask yourself, well, maybe it's just a uniform background of Poisson statistics. And so you can just say, what if it were Poisson with the same total number here? So you hit the button here, and there's what Poissonian would give you. In other words, it's completely consistent with simply some background rate. However, one of those could be the real thing, hence my point. It's one of those experiments where in the end you just apologize for what you didn't find. And maybe you did find something. I hate that. So the next thing we did was we decided that there's this other Ivy League school down the coast there, Princeton, and they have some cool guys. In particular, they have Dave Wilkinson. Here he is. This is Dave Wilkinson doing one of his lesser-known experiments, mainly outfitting their 36-inch telescope to run in parallel with ours. And the cool thing here is that these telescopes are 1.6 milliseconds apart in light time. So first of all, you're looking for a simultaneous hit. And then secondly, it even has to be consistent with the light time. We were measuring to 100 nanoseconds. So we could resolve easily the time delay that should have been expected. Very much like the LIGO experiment, which you know about. So let's see what this one produced. So here's the same kind of chart where number of objects and the number of hits. And you'll see that the number of simultaneous hits between both observatories is 0. That's the kind of experiment I like. Actually, 1 would be better, but at least we don't have to apologize. There was no flash of light bright enough to trigger both those things. All right. So then we got interested in seeing more of the sky. We were looking through a soda straw here. We got into the all-sky experiment. And I'm going to zip through this because time's a-wasting. I want to tell you about the new experiment. We built this observatory. That's Andrew Howard down here. You're going to hear from him these days. Here's our cheap telescope. It's a 72-inch light bucket. It cost us $50,000, including the mount, delivered. And secondary. It's got a 36-inch secondary. How's that for cheap? And there's the building with the roof rolling off. We built some electronics. That's what electronics looks like. We all know about that. And then made some boards. There's a little detector. I learned about those from Dan, too. I learned about everything from Dan. He's great. And I got this slide from Andrew, and things don't just fly in from the left, which is the only thing I know how to do. They can actually do this. That's the chip that Andrew Howard designed to do this SETI. And we ran this thing in transit mode. So here's your cartoon, which is you just point up with this little pixelated array. It had 1024 pixels. The spot on the sky was a declination stripe, 1.6 degrees by 0.2 degrees. That's not a lot of area. And it takes about a year to cover the sky. And because it's transit, you only spend about a minute maximum in that beam. So it covers 0.32 square degrees, about 48-second dwell when you're at zero declination. That's a 0.05% duty cycle. You really like to do a lot more. But I'll show you what we did. We did finally cover the sky. This picture up here is the sky coverage, and all those tiny little red patches are 10-minute observations on each little point in the sky. It gets brighter when we've redundantly screened the thing. So we did the whole sky multiple times over. And wonderful software you get from students. They love to write this stuff. You can see what's going on. You see where the telescope's pointed. You can see a typical interesting event like this where both detectors, beam split, detect a pulse at the same time. That's kind of cool. You even get a picture showing you which pixel it is. It's that pixel and that pixel. But you can't see much with this earlier system because it doesn't have much look-back time, so we designed a new system. Curtis Mead did this. This thing is fantastic. I won't tell you because I don't have time, but this thing finds signals like this, and these things are wonderful because you get look-back, and you can see what preceded it. So this could be the real thing. If we had another observatory, we could tell you better. This is as good as it gets. We have a bunch of these. We call these BICs. That stands for Bastard in Cloud. Those of you who have read the what is it called? The Fred Hawes book. Anyway, we see other things too. How about this? This one takes too long, and it's splattered all over the place. And what that turns out to be is an airplane. So here's an airplane headed straight for our little observation square at that time. We also see things like this, which is clearly not coming from a single point in the sky. And this is due to cosmic rays. Cosmic rays really are the background when you're looking at nanosecond timescales. I see the clock running out, but I'm due for 3 minutes, so.
Gave you 15, so you're now into question time.
Oh, well, I have a question. Tell me about this all-sky thing. Okay, I'll tell you. Anyway, this is a zoo. This is a zoo of cosmic rays, and the last attempt to make simultaneous observations was this, where that's Curtis up here at the Mount Hopkins thing, gamma ray telescope, and here he is running both experiments while he's at Mount Hopkins. So there we finally did some simultaneous stuff. All right. Now the answer to the question. I'm glad you asked it. Now for something completely different. In all these experiments at Harvard, if it's going to cost more than $100,000, we probably don't think about it because nobody's got that kind of money. Well, I'm thinking differently now. So let me just show you. I learned from Dan and from Shelley about these new detectors, which are fast and cheap and proportional. They're called they're multi-pixel APDs, and they look like this. And they give you pulses like this, just a few nanoseconds wide, and they're highly quantum efficient. And you can pave them like this and make a whole focal plane paved with nanosecond speed, 50% quantum efficiency detectors. That is a cool thing. I got a sample of one of these things just Wednesday, put it in a dark box, turned it on, and here's what you get. It's wonderful. These are single photoelectron pulses. Here's 2, here's 3 photoelectrons. Very nice. Look at that uniformity of it. They're marvelous things. So let's design a telescope with these. I'm almost done. Do you use a parabola? Nah, parabolas are fine on axis. You can't even see the point. But once you go off a few arc minutes, they're crappy unless you do correctors. Spheres are bad, but they stay just the same bad. In other words, they're actually good for this. Plus, with these photodetectors, you actually want to spread the light. So I'll show you my design here. It's a 1 meter class F2 spherical light bucket. It's got a paving here of these little array of 3 millimeter square pixels. It covers about 40 or 50 centimeters hexagonal. It's about 22,000 pixels you have to buy, these little detectors, 22,000 of them. They cover about 1.5 times the circle of confusion of the thing, so that's pretty good. Covers 640 square degrees of sky. That's not bad. If you increase it by another 50%, it covers 1,500 square degrees. I got a quote. I said, what do these things cost, Earl, the guy at Hamamatsu? And he said, it depends how many you want. I said, 100,000. Oh, he said, I have to cut the factory. So it turns out they cost $7 a piece. So you need 22,000, that's 150 grand. So one of these telescopes, current price, 150 grand for the detectors, maybe 50 grand for the mirror, I don't know, maybe 100. And off you go. You cover a good piece of the sky. How much of the sky? There's what one of these would cover. Here's what you'd do if you put 8 of these up. Basically, the whole sky from zenith to as far south as you want to go. This is east and west. And if you make them a little bigger, you only need 4 of them. And what you do is you'd make a little observatory like this. This is the M-Earth, a piece of the M-Earth array. But you just put a few of these things up, robotic telescopes, and you let them do their thing. Personally, I'd rather go into the infrared a bit, and Shelley's going to tell us all about that, so I won't, except to say that infrared is probably a better place to be. And my last slide, this really is my last one, really, is, has that detected anything there? How much stake would you put in that? Well, how about if you got that instead? Now, how about if you got both of them, and they matched up, and they even met some kind of prediction? That's pretty cool. 2 observatories is the minimum to claim that you found gravitational waves, and the claim was accepted. Look at this headline. Gravitational waves detected at last, confirming Einstein's theory. If there were only one of those, it would have been, there's a bump in the data, but we see that all the time, and there might be gravitational waves, but nobody knows. Anyway, these are the folks who have helped out, and the sponsors, and all good people, and thank you.
Well, Paul, thank you for answering that question. And we have time for one additional question for Paul. And there will be time in the panel discussion later today. Oh, Ron, OK.
So, Paul, you were very proud of the fact that you could do a 2-telescope experiment with no false positives. But doesn't that just tell you you're wasting signal to noise?
What you would do is you'd basically lower your threshold and accept some small number of simultaneous. You could say you're trading off sensitivity, but I think you're trading off surety as well. Because whatever the sensitivity, the fact that it was received at both places really way, way, way above statistics. And with the timing. But it's like the LIGO. Do you believe the LIGO? Or it means they actually found something, which is really the goal here, isn't it? OK. Anyway, that was the question, right?
Thank you, Paul. Thank you.